Hello students and welcome to another screencast with Mr. Swan. So what we're doing today is we're going to go take a look at some Half-Life notes, and I have a little simulation for you to go use. And then might as well jump right into picture of the day. This is a picture of the SpaceX rocket lifting off that happened over in the Kennedy Center. And then if you didn't get to catch it, this is actually the movie on the bottom right side from that they posted up on YouTube, showing like the live stream of not only it lifting off, some inside the capsule shots of like the astronauts, but also which I think was probably the most impressive, the rocket actually re-landing on a platform in the middle of the ocean by itself, all thanks to computers. So let's go right to it. So SpaceX rocket launch. NASA astronauts Bob Behnken and Doug Hurley are aboard the International Space Station. The pair floated into the station from their SpaceX Dragon capsule at 1:22 p.m. Eastern Time Sunday, 20 minutes after they opened the hatch. They were greeted by fellow astronaut Chris Cassidy, who had been at the station since April, and two Russian cosmonauts. Their arrival completed the last major milestone of the launch that began Saturday when the SpaceX Falcon 9 lifted off from the pad 39A at the Kennedy Space Center. The docking was a delicate and dangerous part of the mission. The spacecraft chased down the space station, traveling in orbit at 17,500 miles per hour, but then approached very slowly in a series of carefully choreographed maneuvers. When they say very, very slowly, they're talking about like a fraction of a meter per second. The mission went very smoothly, ground officials said, following the picture-perfect launch some 19 hours earlier at the Kennedy Space Station. Kennedy Space Center. This is the first, so like why is it such a big deal? This is the first shuttle carrying American astronauts to orbit that has lifted off from American soil in the past 9 years. This is also the first commercial company ever, anywhere, to fly humans into space. Also, this rock then landed back onto Earth safely on a platform in the ocean, moving around, all in under 9 minutes. So that means that rocket then can be used again, which then is really impressive because it saves a lot of money. And then this is like one of the final trials, and then they can actually start bringing astronauts, like more crews up, maybe in crews of 4 in the future. And then from that, they'll continue to get better, and then they can gain money from that, and then they'll build more stuff, and then we'll see what they do after that. So one cool thing that they actually put out, and I thought you guys might actually enjoy, is down here on the bottom, they actually have a link to a docking simulator. And so you can actually go on their website or click the link for it if you like. And you go down here to begin. And so this is like you approaching the space station. And you have to kind of realign yourself by using some of these extra controls to see if you can actually like dock in the space station. Slightly harder than it would appear. It kind of like work its way up there. And then so you can kind of see like a little bit of like what it's like. So I thought that might be a fun thing for you guys to go do. Besides that, let's move on over to the notes. So it'll actually just be a few notes besides today. It won't be too much. We're just doing radioactive and radiometric decay. Or half-life. So like when I was learning this stuff, we just called it carbon dating. It's still a term that's used, but not all the time. The real technical name for it is radiometric or radioactive dating. So radiometric dating is a process where the age of a substance can be determined by analyzing the ratio of certain stable atoms to unstable / radioactive atoms. I don't always break down paragraphs, but we should probably break that down. So radiometric and radioactive are just different words for the same thing. So that's pretty much up here. Is a process where the age of a substance can be determined. When we say age of a substance, we're talking about the age of a past living thing. Something that was at once alive. So maybe like an old plant or tree, or maybe like an animal of some type, usually used with the bone. And we can give from this an absolute amount of time. So whether it was 5,000 years ago, was it 10,000 years ago, 15,000 years ago or so. So we can actually get like a very accurate number. There's like a little bit of a margin of error, but the margin of error is like probably lower than 1%. So it's actually pretty good. And so radiometric dating is the process where the age of the substance can be determined by analyzing the ratio of certain stable atoms to unstable atoms. An unstable atom, another name for it, is radioactive. And so we've heard of radioactive atoms before. A radioactive atom is an atom that will eventually start to lose pieces, you could say, and eventually will transform into something else. And the ratio of a stable atom is an atom that we currently have that just does not change. So that would be like carbon 12. So the carbon that we usually eat throughout the normal day is usually what we call carbon 12. And there are other forms of carbon, like carbon 14. And they will change and start to actually become something else. So we see how much of the like original carbon versus how much that radioactive carbon is in there and what it changed into. We'll go on into this a little bit. So radioactive atoms decay into stable atoms over time. The amount of time it takes for the change can range from a smallest fraction of a second to many trillions of the years. It depends on what atoms you're talking about. So these are all isotopes that we'll be using. An isotope is a radioactive atom. Not technically always, but mostly. And some decay from like a radioactive atom into an actual atom in like truly like a second. Other ones actually take millions of years, some take billions of years, some take hundreds of thousands of years, and everywhere in between. So this process will give us our absolute age, or the exact age of an object. So when you see something in the news being like, hey, they found this like woolly mammoth fossil and it's 6,000 years old, or we found this mummy and this mummy is 4,200 years old. That's how we actually are getting these numbers, is by using this process. And so a little bit, it's actually on the reference table we want to see in the front cover. These are just a couple of the radioactive isotopes. Again, there are like truly thousands of them. But these are just some of the main ones that we're actually using right now. So carbon-14 is a radioactive carbon. When you eat something, there's a very high chance it probably has one carbon-14 atom in it. It's so little, and it's the amount of radioactive energy it gives off is so slight, it doesn't do anything to you. So you actually eat them all the time, and you just never even realize it, and then life goes on. So it's not like a big deal. Like potassium-40. Potassium-40, which you can think of from, everyone always says like bananas. Banana actually has potassium-40 in it, which is radioactive, and you don't notice, because it's just like one tiny little atom. So it won't hurt you. Over time, these radioactive isotopes will change over into something else. So the carbon-14 over time will change into a nitrogen-14. So in short, what we're looking for is we're looking at all the carbon-14 in an object, and then it will start to change. So if we see nitrogen-14 in there, then we know that that must have come from a carbon-14, and we take a look about how fast it decays, and then we start working all this out. So this is more half-life, while a sciencey thing is very heavily into statistics. That's what we use it for. So our half-life, the amount of time, this is so 5.7 times 10 to the third. Remember, that's carrying that decimal over 3 places to the right. So this will take 5,700 years. If you're talking about like uranium, that's 4.5 billion years for it to go all the way down to Pb, which is lead. If you go down to rubidium, this is 4.5 billion. This would be times 10 to the 9th. This is 4.9 times 10 to the 10th. So that's 49 billion years. That's like 3 times older than our entire universe. It does not decay very quickly. And so here's how some of this math kind of works out. Half-life is the term used to describe the probable amount of time it takes for 1/2 of the remaining amount of radioactive elements to change into something else. So breaking it down one more time, half-life is just the term. Doesn't have to be talking about carbon dating or radioactive dating, but usually it is. So is the term used to describe the probable. This is going to be a big one. It doesn't have to be exactly that amount of time. It will be close, but it doesn't have to be exact. So it'll all average out, but it's not going to be perfect every time. It's like thinking about flipping a coin, heads, tails. It's like a 50-50. But if you flip it just once, it's probably, maybe just tails. And if you flip it twice and it comes up tails again, you're like, oh, that's not 50-50 at all. But you have to do it a whole bunch of times, and then you'll see that it eventually will kind of average out. So it's the probable amount of time it takes for 1/2 of the remaining amount of radioactive elements to change into stable elements. And this is a pretty neat thing. So, because it doesn't really go the way sometimes you think it would. So let's say you have an object, you dig it out of the ground. Let's say it's like some type of bone, and you have 100% carbon-14, 0% nitrogen-14. That means that object was pretty much died today, because it's not intaking any more new carbon. So that carbon that's in there kind of hangs around and gives it time to actually eventually decay. So if you see something and you register this usually with like machine, and it's like 100% carbon-14, it means it's most recent time. It's like a tree in the forest just falling over almost immediately. If you wait 1 half-life for carbon, so 5,700 years go by, it goes down to what you expect it would be for like a half-life, right? The carbon has reduced by half, and the carbon that has reduced by half has changed into nitrogen-14. So if you saw the bone, let's say, I kind of forgot what our example was. Let's say it was actually like a bone. from our first part for 0 years, it's whatever it looks like. If you look at it again 5,700 years later, it's going to look exactly the same. You won't notice that it actually went through any change at all. You can't see this with your eyes. So it's not like the bone disappears. It's just that the atoms inside have started to change. And so the carbon-14 has gone down by half. The nitrogen-14 has gone up by whatever it was reduced by. So this one, carbon-14 went down from 100 to 50. So the nitrogen-14 went up to 50. And so this part, I think people are usually pretty good at. They're like, okay, so half-life is the amount of time it takes for a radioactive element to decrease to something else. And then they see this kind of first example, and they're like, okay, so carbon-14 is 5,700 years, and it goes down to half, which makes sense. It usually is the next step that kind of starts to get people, because it's not reduced by half. It is reduced by half of the remaining amount. So if you wait another 5,700 years, and this one has gone down by 50%, you might assume that the next carbon should be 0%, but it's not. It goes down by half or whatever it was. And that is usually the big jump that people have the most trouble with. So this going down from 100 to 50 is reduced by half. And then it gets reduced by half again and goes down to 25. So it only lost 25% here. Or here it lost 50. And if you do it again, well, now it's going to go half of the 25. So that's 12.5%. And it goes down again. As you might expect, is this like a fast process to give it to go to 0? No, it's going to take a long time for it to get to 0. Because after 12.5%, well, now it's going to go down to 6.25%. And then you have 3.125%, right? And then eventually down to like 1.5%. And then it goes down to like these fraction of percents. And it takes a long time for it to eventually go down to 0. And it eventually will. But it's going to take a while. So this is the textbook perfect example of half-life and the amount that it's actually going down. In the meantime, nitrogen's going up. And so it continues to go on up. Carbon's half-life, so this becomes a problem. If you're using a machine, it can pick up these atoms. If it can only go so small. Like the amount can only go so tiny before we really have a hard time picking it up. So after a whole bunch of half-lives, when it gets to about like 60 or 1,000 or so years ago, you can't really use carbon anymore because the fraction of carbon is so tiny the machine could miss it. And so we just can't use it anymore. So what would we do instead? Well, you would use, if something's really old, like that old, you would use an atom that decays at a slower rate. And that's pretty much what we'll kind of jump to for this. So I think it's good to kind of review. That's pretty much like it for the slides. If you want to know more about this one, I'm not going to go over this, but the next slide is kind of like exactly why do these carbon-14s even happen? You know, like where does this actually even come from? This slide kind of goes into that one, but I'll let that for your reading if you're interested about this. Some of this I think is good to read, and then you need to like experience it. You know, you have to kind of take a look at it. So for that, I have a gizmo for you to kind of go look at with today, and then the next lesson will kind of go more into half-life as well. And then this is what a half-life would look like if you played it out. So this is what the simulation is. So you have my radioactive atoms, which are the red. Daughter atom just means a stable atom. So it goes from radioactive into the daughter. So it's like what it's becoming like in the past. You almost think of a radioactive atom as like a parent. There's no such thing as a son atom. And so if you play this, that's it decaying. The idea of it. So you have all these atoms together, like let's say they're all carbon-14, and they're just going. They're just decaying. Now, the big issue, and you kind of like let this go on, let it eventually go down to 0, is that it will eventually go down to 0. It just takes time. And it's probably going to be a couple questions, which I already know you'll have, but let's take a look at the graph. If you were to graph this, those graphs look like this. They kind of like the nice kind of sloping curve right here. Where if you were to graph the opposite, the daughter atoms, they would have a mirror graph. And it would kind of go up just like this. And so you can actually take a look at how this goes. And if you wanted to restart this one actually is random. It always kind of plays out just about the same. It's not perfect. That's why you see these like little bumps on the graph right here. Right? And the atoms that were decaying are different this time than it was like last time. But it generally always works out to this point. And so when we take a look at an object, and you might say like, okay, well, I found this bone and it's not going to have exactly 50-50%. Let's say it has 60% carbon and 40% nitrogen. Well, you make this graph out. right? And this would be time. And we know the half-life would be like, so it's going down, let's say, let's make another one. Let's make it exact numbers. So let's do 100. There, hit play. And it decays down. So for one half-life, it would have to go from 100 to 50, like right here. And the amount of time that would take would be right here on this line would be one half-life. Would be right here. If you were going to write it in. And that would be 5,700 years if this was carbon. So if you found something that was 60-40, well, you just go up to the 60. And then you go down. That just happens to be like a tinge below, before like where the one half-life would be. So that means it has to be like a little bit before 5,700 years. And so that's actually how we look. We get this ratio. And the ratio is never exact. It's never 50-50 or 75-25. Not usually. It's always like a little bit before or after. But you just find out where those ratios would be on this graph. You go down and it shows you where the time is. And really, half-life at the end becomes as easy as that. You find the ratio, go to the graph, look down at the x-axis, and tells you how long ago this object was alive. And so we've been doing that. That's how we find dinosaur fossils. And that's how we figure out ages, like some of these absolute ages. We use carbon dating. And half-life is a term that sometimes it comes up even more and more. I've heard it being brought up for even like the COVID pandemic, because they'll take a look at an object and they'll see how long can COVID survive, or that virus survive on an object like paper. And so they usually use half-life as well. So it's not becoming radioactive, but how long does it take for half of it to actually go away? And for paper, it's 30 minutes actually. So it's actually, yeah, paper kind of kills it pretty quickly. And so that is my half-life spiel for you. So go on, use the gizmo a couple of times to get kind of used to it. Next time I'll have like a bigger simulation for you actually to use on your next lesson, which is on Wednesday. And go through and take some of these notes. This is going to come on up often. Half-life is used a lot. It's used a lot in chemistry as well. So it will be good for you to learn it to prep yourself for next year. Besides that, that's all I have for you today. And so goal, play with that SpaceX simulation docking game, which I think is kind of neat. It took me 3 tries actually eventually to land it. See if you can beat that. And then use the gizmo, the half-life one. There's like 5 questions below to kind of like answer, to kind of get yourself kind of used to this. And then that's it. Okay, besides that, have a great day, everyone. See you later.